Okay, so in this video we'll look at some more examples of relations. So we're really building ideas on top of ideas. So it might be the case at this stage that if you're a little bit lost and you're still watching these lectures, you might think, oh, I should go back and watch the previous lectures. Not necessarily. What you should do is go and do some exercises at this point, try and help you understand. Okay, so let's see what we have here. So we've got a set U containing 0 and 1, and we have this thing here, it's subset of, and it's the set of ordered pairs xy, where xy are subsets of U and x is a subset of U. Now what we might do is write down all the subsets of U anyway, because that's what these objects are. X and y are subsets of U. So we'll write down all the subsets of U. So the subsets of U, and the way you can think about this is, remember, a subset is you go through each of the elements and you say either yes, I include it in the subset, or no, I don't. So suppose you say yes to both. So that will give you a subset, the set containing 0 and 1, which we call U. How about then I say yes to 0 and no to 1? That would be the set containing 0. And what about if I say no to 0 and yes to 1? That would be the set containing 1. And finally, what if I say no to 0 and no to 1? Then that would be the empty set. Okay. Now alternatives for writing U and the empty set, you could write U is the set containing 0 and 1, and you can write that the empty set is the set containing no elements, but do not write that this is the set containing the empty set, because this is not an empty set. This set contains the empty set, has one element, so don't use this. Okay, so the things that we're doing, what is the relation on? So a relation is a subset, and I have to be careful now. So this is going to be quite complicated. But I mean, you're building ideas on top of ideas. So it's an element of subsets of ordered pairs, some ordered pairs. So you see what I mean about ideas on top of ideas. So it's an element of the subsets of U, Cartesian product subsets of U. Now that's kind of complicated, but all it means is some ordered pairs. You see, X and Y are elements of this. The first thing in this, the second in this, and it contains a subset. So it's a pair of elements from here, both of them in here, such that the first one is a subset of the second one. Okay, so now we have to list all the subsets. Right. So we'll take our time. I mean, you can kind of do it a picture actually could help here. And we might draw some pictures in a minute. Actually, we'll do the pictures now. Okay, so let's draw U. Actually, will the picture work? No, I'm not so sure of the picture. Okay, so let's say, okay, the way we'll do it is we'll say what's related to U, what's related to the set containing 0, what's related to the set containing 1, and what's related to the empty set. And something is related to something if the first thing is a subset of the second. So to ask what is related to U is to basically ask what are the subsets of U. Okay, so subset of, now normally I'd probably just write this symbol instead of subset of, but this is what we have here. So it is a set of ordered pairs. So what is a subset of U? Now here, of course, we've listed the subsets of U, so all of these are subsets of U. So for example, UU works because U is a subset of itself. Also, the set containing 0 is a subset of U. The set containing 1 is a subset of U. And the empty set is a subset of U. So the real difficulty here actually is probably understanding the notation. So subset of, it's a relation, so it's some ordered pairs such that the two things in the ordered pair are subsets of U, so they have to be a pair of these things such that the first thing is a subset of the second thing. So U is a subset of U, set containing 0 is a subset of U, set containing 1 is a subset of U, and the empty set is a subset of U. Okay, now what might be worthwhile is to actually list the subsets of this and the subsets of this and the subsets of this. And we can probably do that down the bottom here. So what are the subsets of the set containing 0? So remember, a subset is, it's a selection of elements and you go through each element in the set and you say yes or no. Now here there's only one element, so you just say yes, in which case you just get the set containing 0. Or you say no, in which case you get the empty set. So that's the subsets of 0. That's all, yeah. Now what about the subsets of 1? So this P means the subsets of this set. So again, the answer is either yes or no for the element 1. So if you say yes, you get the set containing 1. And if you say no, you have the empty set. Now the last one is the trickiest one in a way. So what are the subsets of the empty set? Now there's nothing to go through here. So there's no elements to say is it an element or not. So essentially the way I was doing it doesn't really work because you've got nothing to choose. So like you don't want to say, you'd be tempted to say that the set of subsets of the empty set is actually the empty set, that there are no subsets. But the way we define subsets, it's kind of, it's this difficult thing, it's called vacuously true. It says that if something is in the first set, an element of the first set, then it's automatically in the second set. But the starting point, if something is in there, if that's not true, then the second bit is called vacuously true. So it's a bit tricky, it's a bit confusing. You might do a little bit of it in semester 2 in your maths module there where they do a lot of logic. But if you follow it through, and I could spend a lot of time working on it, it's probably more a semester 2 thing. But an empty set, through it, an empty set is always the empty set is always going to be a subset of something else, but also the empty set is a subset of itself. Okay, so these are our subsets. So we'll keep listing now. What is related to the set containing 0? Subsets of the set containing 0. So the subsets of 0 are 0 and the empty set. So we're going to have the set containing 0 is a subset of 0. And the set containing the empty set, sorry, it's not the second, it's the empty set, is a subset of the set containing 0. Similar story, we have the subsets of the set containing 1 are the subsets of the set containing 1 and the empty set. So we have that set containing 1 is a subset of itself, and the empty set is a subset of the set containing 1. And finally, the subsets of the empty set is a subset of the empty set. So quite tricky. If you could do this question yourself, you really are doing quite well, because you've got layers and layers of different things on top of itself. You've got the subsets, you've got the ordered pairs, and you have a relation. And if you go through it, this is everything. So U is a subset of U. Now I'm just going to say 0 and 1 because it'll take too long in other words. So 0 is a subset of U, 1 is a subset of U, the empty set is a subset of U, 0 is a subset of itself, empty set subset of 0, 1 subset of itself, empty set is a subset of 1, and the empty set is a subset of the empty set. So that's all the ordered pairs. Now I think we're going to graphically look at that. So this is represented well by what's an arrow diagram. Okay, so let's see what this arrow diagram should look like. So you put all the inputs are the things in the first pair, and the output is the thing in the second pair. There's also something called a lattice diagram, which we might draw as well. Well, no, we won't, because maybe it's confusing things. Okay, so we put all the things, like the two subset are, the target and the source, subsets of U, and what are in there? Well, we've got U itself, we've got the set containing 0, we've got the set containing 1, and finally we have the empty set. And it's going to U, set containing 0, set containing 1, empty set. So you draw an arrow between things that are related. So U is a subset of U, and that's it. 0 is a subset of U, and 0 is a subset of itself. 1 is a subset of U, and 1 is a subset of itself. And the empty set is a subset of itself, maybe this isn't the best way to do it, and of 1, and of 0, and of U. But that's what an arrow diagram is. Yeah, probably not the best way to represent this. But anyway, okay, let's look at the second part. Let's strict subset B. It's the same thing that X and Y are subsets of U. I think it's actually missing something here. So what it's missing is that X is a subset of Y, but it's not equal to Y. So it's a strict subset. It's strictly smaller. This is kind of like less than or equal to versus strictly less than. So list all the other pairs. Now it's going to be the same thing because it's subsets, but you don't include, you don't put it in ordered pairs that are where the two subsets are equal. So U is not going to be there, 0, 0 not going to be there, 1, 1, empty set is not going to be there, but everything else. So I'm just going to list off those same ones. So this is strict subset of is equal to, so all the ordered pairs, but not 0, 0, yes, set containing 0 and U, yes, set containing 1 and U, yes, empty set and U is a strict subset, 0, 0, no, because they're equal. Empty set is a subset of 0, I want to include that. And empty set is a subset of the set containing 1, I want to say that. But there's no more, because, yeah, there's no more. So this is set containing 0 is a subset of U, not equal. Set containing 1 is, remember, U is the set containing 0, is the set containing 0 and 1. This is a subset but not equal. 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 Now, probably the way to, if you want to draw any relation, I probably should have done it with the other one, is use a digraph. So for a digraph, the objects, as it were, get nodes. So there'll be 4 nodes here. So that'll be for the empty set. That can be for the set containing 0. That can be the set containing 1. And then U. So U, set containing 1, empty set, set containing 0. And you draw arrows between things that are related. So set containing 0 is related to 1. Set containing 0 is related to U. Set containing 1 is related to U. So draw an arrow. The empty set is a subset of U. So draw an arrow. Empty set is a subset of U, draw an arrow, and empty set is a subset of 1, draw an arrow. Now if you leave out that thing, it's what's called a lattice diagram. If to do the other one, subset of, I would just have to add loops, because they're all subsets of themselves, not strict subsets, but subsets. And then you've got some properties that this has. So if I did include the loops, so if I wrote the digraph of this, there'd be 2 properties you'd see. Everything is related to itself, and the other thing is the property of being transitive. Now a transitive basically says if say A is related to B and B is related to C, then A is related to C. It's like a property less than has as well. If say 1 is less than 2, 2 is less than 7, so 1 is less than 7. Okay. Right. So another example of a relation. Now this one's a bit harder, but let's look at it. So consider a relation on OR. Now, OR, remember, is just your real numbers, is basically the number line, all possible decimal numbers, positive and negative, including zero, including whole numbers, including fractions, including everything. And a relation on OR means a subset of OR Cartesian product OR, set of ordered pairs, because remember, a relation on OR will contain things like, I'm just trying to think here. So I think square root of 5 is related to 0 here. So it's a set of ordered pairs. So y is square root of 5 related to 0, we'll see in a moment. And the set of ordered pairs of real numbers is the plane. And it's not going to be the full Cartesian product. It's not going to be the full relation. A relation is a subset of it. So it's going to be sum of the points on the plane, which is often a curve. Okay, so it says that two numbers are related. Now this OR is not this OR. This OR is the name of this relation that we're talking about. OR is the set of real numbers, the number line. So a pair of numbers, x is related to y, if and only if x and y satisfy this equation. So for example, if you look at this, x being square root of 5, y being 0, x squared is root 5 squared, which is 5, plus 3 times x times y squared. Now y is 0, so that's 0, plus 0 cubed is 0, so you end up with the square root of 5 squared equal to 5. So this pair of numbers satisfies this equation. So this pair of numbers, square root of 5, is related to 0. So a pair of numbers, x and y, are related if they satisfy this equation. We could call this then the equation of the relation. And this is the sense that you might remember from school, the equation of a line, the equation of a circle. This is in the precise sense. A point is on the line if and only if it satisfies the equation of the line. A point is on the circle if and only if it satisfies the equation of the circle. And both of those things, the line and the circle, are like relations, because think about a line, all the coordinates on the line, they're all ordered pairs. It's not all the ordered pairs, it's some of them. So a line is a relation between real numbers. A circle is a relation between real numbers. You can graph these things using computer software packages, and it'd be interesting to kind of think, how could you implement that yourself? This is going to use a thing. So we have got, this is what you end up with. So these are the points, the coordinates that satisfy the equation and so are related. And this is the graph. Now this isn't the digraph, this is, I'm going to call it the coordinate graph of the relation. So I think we had a point square root of 5, 0. So that's here. That satisfies the equation. So it's on the coordinate. It's in the so if it satisfies the equation, it's square root of 5 is related to 0. So the coordinate graph is plotting all of the ordered pairs in the relation. So square root of 5, 0. Another one might be 1, 1. So if you look back at this, put in x equal to 1, y equal to 1, you get out 5. So 1, 1 satisfies the equation. So 1 is related to 1. So in the coordinate graph, you plot 1, 1. And then, like, there's people are in pure maths are interested in questions like how many components are there in the coordinate graph? Does it intersect itself? And all manner of different questions. Okay, that's probably more technical than what we're going to see. Now, at the moment, there's only some small questions about relations. There's harder ones down here. These starred questions are harder. Focus on these first, get comfortable with these. It's probably no problem to find these difficult. You should give them a go. If you can handle these, you're doing well, but they all require some thought. Okay, so we're going to look now at some properties of relations. Okay, so let's see. When you want to study some idea like relations, you want to look at some properties. Okay, so relations on a set A are relations between A and A. In other words, subsets of the Cartesian product of A and A. And this just means subsets of this just means some ordered pairs. First thing in A, second in A. If A is finite, you can do a digraph. Like, you have no hope of doing a digraph here. If you think about it for even any amount of time, it's not going to be possible. Each element is given a node, And if A1 is related to A2, then an arrow is drawn between A1 and A2. Okay, so here's a relation on ABC. Now the full Cartesian product here will have 9 elements. This a relation 1, 2, 3, 4, 5. It's just sum of them. So that's all a relation is. Sum ordered pairs. Right, so let's do the digraph. So there's 3 nodes. Let's say A, B, C. And we draw arrows between nodes of elements that are related. So we got A is related to A. We have A is related to B, and we put a direction because just because A is related to B, we don't actually have B is related to A. Okay, B is related to B, so that's a loop. C is related to B, and finally C is related to A. So this is the digraph and the best way to analyze a relation when the relation is on a finite set. Okay, if a relation R is such that every element of A is related to itself with a loop, so that for all elements in the set, everything is related to itself. Now, it's very, very important. It's not the case that if you've some things related to themselves that the relation is reflexive. Like, there's no point in saying that A is reflexive or B is reflexive. Every single element has to be related to itself, and it's the relation that is reflexive. So the relation is reflexive. A is not reflexive, B is not reflexive. This graph is simply not this relation is not reflexive. Everything has to be. Okay, so for example, the relation above is not reflexive as C is not related to C. There's no, you can just say it in different ways. You can say CC is not in the relation. You could write C is not related to C. So write C or C and then slash out the, it's like not equals, not related. Or you can say there's no loop at C. Okay, so consider this relation on the set 1, 2, 3, 4, given by A is related to B if the first number divided by the second number is a natural number. Okay, so let's do this. So we got, now we might list the ordered pairs afterwards. Yeah, we'll do that because I'll do the diagraph. So I have the elements 1, 2, 3, 4. Okay. Now, we ask, is 1 related to itself? Is it related to 2? Is it related to 3? Is it related to 4? So is 1 related to itself? It is if 1 over 1 is a natural number in the set of natural numbers. 1 over 1 is equal to 1. So 1 over 1 is a natural number, so 1 is related to 1. We also have 1 is 1 related to 2? No, because 1 over 2 is a half, is not a natural number. Similar story, 1 is not related to 3 because 1 over 3 is not a natural number. Is 1 related to 4? No, because 1 over 4 is not a natural number. Now let's look at 2. What's 2 related to? Is 2 related to 1? Yes, 2 is related to 1 because 2 over 1 is equal to 2 is a natural number. So we draw an arrow. Is 2 related to 2? Yes, because 2 over 2 is equal to 1. So draw a loop. Is 2 related to 3? No, because 2/3 is not a natural number. Is 2 related to 4? No, because 2/4 is not a natural number. What about 3? Is 3 related to 1? Yes, because 3 divided by 1 is equal to 3. It's a natural number. Draw an arrow. Is 3 related to 2? No. Is 3 related to 3? Yes, because 3 divided by 3 is 1, which is a natural number. We'll draw a loop. And finally, is 3 related to 4? No, because 3 over 4 is 3/4 is not a natural number. Now let's go with 4. 4 over 1 is equal to 4 is a natural number, which means 4 is related to 1. 4 over 2 is equal to 2, which means that 4 is related to 2. 4 over 3 is not a natural number, so 4 is not related to 3. And 4 over 4 is equal to 1, so 4 is related to 4. Now what we might do here is just write down the ordered pairs here. So this relation is equal to, let's see, 1 is related to 1, and that's it. 2 is related to 1 and itself. it's not related to 3, and it's not related to 4. See, the arrow doesn't go that way. What about 3? 3 is related to 1, and 3 is related to itself. 3 is related to 1, 3 is related to itself. And finally, 4 is related to 1, 2, and itself. 4 is related to 1, 4 is related to 2, and 4 is related to itself. Okay, there we go. So this thing is reflexive. Now, there's 2 ways of answering it. You either say you say every, now it has to be every node. It's not good enough that 3 out of 4, every single node must have a loop. So every node has a loop. And then the other one I think is a bit harder to write down, because you have to say for every element in S is related to S, like 1 related to 1, 2, 2, 3, 3, 4, 4. You could say maybe there is a compromise where you say every element related to itself. And then the hard thing would be to say that for all S in S, for every element of the set, you could write S or S related to S, or I like the ordered pairs, S is related to S is in the relation. And this R is not the real numbers.